Welcome to Mathematical Physics. Today, we are going to explore a fascinating topic, the Cauchy-Euler equation. If you have ever wondered how to solve differential equations with variable coefficients without getting lost in infinite series, you are in the right place. Let us dive in. Before we look at the math, let us understand why this equation matters. Normally, when a differential equation has variable coefficients instead of constant numbers, it becomes incredibly difficult to solve. We often have to rely on complex infinite series. But the Cauchy-Euler equation is a beautiful exception. It is highly symmetric, allowing us to find an exact solution easily. In your physics journey, you will see this equation whenever a system has spherical or cylindrical symmetry, like calculating the electric potential around a sphere, or solving the Schrödinger equation for the hydrogen atom. Now that we know its importance, what makes an equation a Cauchy-Euler equation? The defining characteristic is that the power of the independent variable, x, exactly matches the order of the derivative it multiplies. Think about the intuition here. Every time you take a derivative of a polynomial, like x to the power of m, the power drops by 1. But if you immediately multiply it by x, the power goes right back up to m. This mathematical synchronization is a huge hint. It suggests that our trial solution should be a simple power function. This brings us to the formal definition. Here is the general nth order Cauchy-Euler equation. Notice how the nth derivative is multiplied by x to the power of n, the n-1 derivative by x to the power of n-1, and so on. The a sub n terms are just constant coefficients. When x increases, the variable coefficients grow, but the structure ensures that a simple power function will balance perfectly across all terms. Before we move on, let us see this intuition with a concrete example of our trial solution. We guessed that y equals x to the power of m. When we take the first derivative, we get m times x to the power of m-1. If we then multiply this derivative by x, as the Cauchy-Euler equation dictates, the x and x to the m-1 combine. The power is restored to m. This confirms that substituting y equals x to the power of m will transform our complex calculus problem into a simple algebraic puzzle. Now that we understand the general form and our trial solution, let us look at the most common case you will face, the second-order Cauchy-Euler equation. Here, the highest derivative is the second derivative, multiplied by x squared. The constants a, b, and c define the specific physical system you are studying. If a, b, or c change, the behavior of the solution will shift dramatically, as we will soon see. Let us apply our trial solution to this second-order equation. We're given the trial solution, y equals x to the power of m. We need to find the first and second derivatives to plug them into our differential equation. The first derivative is m times x to the power of m-1. Taking the derivative again gives the second derivative, m times m-1 times x to the power of m-2. We now have all the pieces required to substitute back into the main equation. So we have our derivatives. This brings us to substituting them into the original equation. Watch what happens to the x terms. We plug in our expressions for the second derivative, the first derivative, and the function itself. Next, we multiply the x terms together. X squared times x to the m-2 perfectly simplifies to x to the power of m. Similarly, x times x to the m-1 becomes x to the power of m. every single term now contains x to the power of m. Continuing from our previous step, we can now factor out x to the m completely. For the solution to be non-trivial, x to the m cannot be 0. Therefore, the expression inside the brackets must equal 0. We expand the first term to get a times m squared minus a times m. Grouping the m terms together yields a simple quadratic equation, am squared plus b minus a times m plus c equals 0. This is called the characteristic equation, and it is the key to finding our final solutions. Now that we have derived the characteristic equation, let us look at how it works. It is just a standard quadratic equation in terms of m. Just like any quadratic equation you've solved in algebra, it will yield two roots, which we call m1 and m2. The mathematical nature of these roots is crucial because it dictates the physical behavior of our system. Depending on the roots, we divide our solutions into three distinct cases: distinct real roots, repeated real roots, and complex roots. Let us examine the first case. This happens when the quadratic formula gives us two real, distinct numbers for m. The general solution is a straightforward linear combination of x to the power of m1 and x to the power of m2. The constants c1 and c2 are determined by the specific boundary conditions of your physics problem. Physically, this represents pure polynomial growth or decay, depending on whether the roots are positive or negative. Before we move on, let us see this with a concrete example from our solution curves. Suppose our characteristic equation gives us roots of 2 and 0. We substitute these into our case 1 formula. The x to the power of 0 term simply becomes 1. If we set our boundary constants such that c1 is 1 and c2 is 0, we are left with y equals x squared. This represents pure polynomial growth, a very common result in physics. This brings us to case 2, where the roots are real but identical. A second-order equation requires two independent solutions, but we only have one root, m. To find the second solution, we use a technique called reduction of order, which tells us to multiply the first solution by the natural logarithm of x. So our general solution becomes a combination of x to the power of m and x to the power of m times the natural logarithm of x. Let us apply this to another example. Imagine our characteristic equation gives us a repeated root of exactly 1. We plug m equals 1 into our case 2 formula. To isolate the unique behavior of this case, let us set c1 to 0 and c2 to 1. This leaves us with y equals x times the natural logarithm of x. Physically, this represents logarithmic linear growth, which grows slightly faster than a pure linear function due to the natural log term. Finally, we have case 3, which occurs when the quadratic formula gives us complex conjugate roots, alpha plus or minus I times beta. Using Euler's formula, we transform imaginary powers into sine and cosine functions. The real part, alpha, acts as an envelope, determining if the wave grows or decays. The imaginary part, beta, determines the frequency of the oscillations. Because the sine and cosine depend on the natural logarithm of x, the waves stretch out as x increases. Let us see how this oscillatory behavior looks mathematically. Suppose our roots are purely imaginary, meaning alpha is 0 and beta is 5. We substitute these into our case 3 formula, Because alpha is 0, x to the power of 0 is 1, meaning there is no growth or decay envelope. If we set c1 to 0 and c2 to 1, we get y equals sine of 5 times the natural logarithm of x. This represents pure logarithmic oscillation. Now that we have calculated these examples, let us look at them visually. On this graph, the horizontal axis is x, and the vertical axis is y. The blue curve shows case 1, pure polynomial growth, sweeping upwards as x squared. The red curve is case 2, logarithmic linear growth, rising steadily but less steeply. The green curve is the most fascinating, case 3. Notice how it oscillates like a sine wave, but the distance between the peaks gets wider and wider as x increases. This stretching happens because the oscillation is with respect to the logarithm of x, not x itself. So, we have proven that the trial solution works beautifully. This brings us to an alternative method. If you feel uncomfortable just guessing that y equals x to the power of m, there is another brilliant way to solve the Cauchy-Euler equation. We can use a clever change of variables. By substituting a new variable, we can magically convert the difficult variable coefficients into simple constant coefficients. Once transformed, you can solve it using standard methods you already know from earlier in your course. Here is the substitution that makes this magic happen. We set x equal to e to the power of t. This changes our independent variable from x to t. As x increases, t grows logarithmically. By applying the chain rule with this substitution, all the x terms in the original differential equation cancel out, leaving an equation with only constant coefficients. It is a powerful mathematical trick that connects the Cauchy-Euler equation to standard linear differential equations. Let us see how we finish this alternative method. Once you have solved the transformed equation, your answer will be in terms of t. But the original problem was in terms of x, so we must reverse the substitution. We start with x equals e to the power of t. Taking the natural logarithm of both sides, we find that t equals the natural logarithm of x. You simply replace every t in your solution with the natural logarithm of x, and you arrive at the exact same final answers we found earlier. We have covered a lot of ground today. Remember, the Cauchy-Euler equation is defined by the power of x matching the order of the derivative. By using the trial solution, y equals x to the power of m, we turn a complex differential equation into a simple quadratic characteristic equation. Depending on the roots, your system will show polynomial growth, logarithmic linear behavior, or beautiful logarithmic oscillations. You now have all the tools to solve these equations confidently in your physics problems. Great job!